So a very good afternoon to all the students and the faculty present today, and to all the members of the LTA lab. My name is Shashwat Trivedi, and this session we are going to have tutorial number 3 is on mass breakdown estimation. So whatever is left now, that is the masses of the avionics, then the payloads, as well as the estimation of CG. And then we're going to look at the breakdown of all the components of the airship that we have calculated until that point. So that will bring us to the end of our design methodology exercise that we had intended to. So a little bit about me. So I have a dual degree in aerospace from IIT Kanpur. I was the coordinator of the Society of Automotive Engineering chapter there. And technically, I was involved in the suspension subsystem of the Formula racing car. I have worked in a startup, performed CFD simulations to design a novel water filter that was based on the principles of fluid mechanics. I have worked in ITK on a project funded by Indian Railways, and we simulated the manufacturing processes, the stresses, and all those parameters that we get when the side walls of train coaches are manufactured. And currently, I am a PhD research scholar at the LTA Systems Lab, and my research involves application of fuel cells, as well as I'm also looking into AI and ML in airship design optimization. So let's quickly go ahead to what we have done until now. So we have computed drag, right? So what was the last thing that you got? From drag, we arrived at something, at a very crucial parameter. Can some of the students tell me, please, what was the last thing that we arrived at?
Drag computation.
Right. So you got thrust from there, right?
Yes, sir.
So basically, we start with thrust from this point. And now what we're going to look at, we're going to look into the selection of the electrical motors. And so meaning we're going to look at what would be the weight of the motors. Similarly, we're going to look at the batteries and avionics and their weights. And finally, as we said, we're going to look at the payloads, and we're going to end this exercise. So let's look at the estimation of the mass of the motor, of the electrical motor. So we already have thrust, as you rightly said, and which was 310.38 grams. I hope you have these figures, but still they're on the screen. So these figures will now come down of use in your calculations. I hope all of you have your calculators and your pens ready with you, right?
Yes, sir.
And I also hope that your energy is not down by lunch, rather does serve the right purpose. So this graph is like, so this is a graph of weight versus thrust for different motors from a company called Turnigy. So different motors were plotted, and there was a line fitted, and this is what we obtained. So this is simple enough, but there's something curious to notice here. Are you able to spot that? I hope my mouse is visible. So our thrust, see the order of magnitude of our thrust and the order of magnitude of the thrust on the x-axis. Do you see a difference?
Yes, sir.
So which means we are dealing on this graph, we are dealing with thrusts of a very large order of magnitudes, right? But our thrust is of a lower order. But thankfully, there are values here which are actually low. But strictly speaking, we would actually not get a value which would be very, very precise. So remember that we will have a value which will have some margin of approximation in it. So this graph is actually a fit, and when we fit that equation, this is what we get. So the motor weight comes out to be 0.0725 times the thrust required plus a constant 16.155. So I put the thrust required there for you and request you to please tell me what would you get as a motor weight.
So 38.65.
38.65.
Great. So we have 38.6 gram. So here you got a motor. So see, again, it's very down below here, right? So this is something to just keep in mind. And also remember, this is an exercise where this is an initial sizing exercise. So like we have to make some kind of assumptions or some kind. So it's like we have to go with something, right? So currently we're going on with these curves. Again, now you might use LiPo cells, right? LiPo batteries. So now you know for every battery there may be different number of cells in each battery. So when you look at different batteries, so what we observe is that for different magnitudes of thrust, the number of cells also goes up. So you may have a 2-cell, 4-cell, 8-cell, or a 10-cell battery going up to that. So now we got to select based on a value of thrust, how many number of cells do we need? Is it clear? Is the graph clear to all?
Yes, sir.
So this is again obtained from the same company, Turnigy.
Yes, sir.
And this is the equation that we get. So when we put thrust there, can you please calculate the number of cells that would be required for the thrust that we have?
Two point
2.30.
7.
Great. So what I get is 2.31, but it's okay. We are not bothered about the second decimal. But definitely there's something curious here, right? It's 2.3. It's not 2 or 3. So,
Yes.
so now what? What do we go with? 2 or 3 or something else?
3.
3. Okay. And why? Do you have any reason? Like anything that comes to your mind? Why 3?
Sir, we should keep the power a bit extra power with us.
Yeah.
Good for backup.
Fair enough. That's a fair enough reason to select 3. So, but this is where it gets a little interesting here. So I would say we hold this argument at this point, and we'll again take up this argument later. What to select, 2 or 3. So right now I just kind of agree with you. Let's go with 3. But let's see ahead. What's more. So now we have the thrust. We have the weight of the motor and the number of cells in the battery. Now, whenever we talk of any electrical equipment, so the motor is going to be connected to the battery, right? So there's a very important electrical quantity which any electrical calculation involves. And what that is? A very basic electrical quantity. And we have talked of in the mechanical, like in mechanics we talk of speed, right? In electricity we talk of, any guesses?
Voltage.
Correct,
No.
but voltage, so something with current actually, right? So now next thing what we need is the current. We need to calculate the current that needs to be supplied to our motor, and also we are going to look at what the propeller diameter should be. After all, you are estimating the avionics, right? And avionics is not complete without the propeller, right?
Yes, sir.
So we start off with a thrust, and and there's something more. So every electrical motor that you have. So first of all, I may just like to ask you, how many electrical motors do we actually have in our airship? Do you remember? How many motors do we need?
So we will need 3 motors.
3 motors.
Correct. And can you please quickly name the
3.
exact, then the name for like the purpose of them?
3.
One
Sir,
is
for
for
3-axis control, we'll need brushless
Yeah.
motors.
Yeah, so one for thrust, one for the lift or the attitude control, and another for you can say this, the yaw, right? Great.
Yes,
So
sir.
for every motor, we need to install an electronic speed controller. And so because that is what ultimately transfers the inputs to the motor, right? And the electrical speed controller consumes some current. Also, there might be some other equipment. So we assume a 20% margin that is extra for the current that we will have. We'll add 20% to it, right? So again, from Turnigy, we get a graph, we get a plot for various motors and of varying values of thrust, and we get a like current corresponding to every thrust value for different motors, and we get a logarithmic curve actually. The logarithmic curve has this equation, and when we substitute the value of thrust, I'd again ask you to please calculate what is the current that will be required for the thrust that we have. Remember, it's a natural log.
Six 6.263.
Great, that's correct. So we get 6.26 amperes, and taking a margin of 20%. So we just increase it by 20%. So we get 7.52. I'll request you to note down this number 7.52 because this is actually the net current that we have. Okay, so our motor needs to be supplied this much amount of current. Next thing, what propeller size do we need? So again, from Hobby King, we get this graph between thrust and propeller diameter. Again, a logarithmic curve, and the same exercise. Please, could you again calculate what is the diameter of the propeller which would be fitted to our motors?
Six 6.663.
Great, but you're answering very quickly. Do others? I have others stop calculating because just one student is answering.
No, sir, we are
Yeah.
calculating, sir.
Have others got the same?
Yes, sir.
Okay, so we get 6.6 inches. This was in inches actually. So we are done here with our motor. Also, we know how many cells do we need in our battery, but we are not done with the battery yet, right?
Yes, sir.
Let's go on to battery and the remaining avionics. At this point, I would like to engage you in a little discussion. So let's talk of avionics at this point. So what do you think would constitute in the avionics? What all would be the components of the avionics in our airship?
Sir, we'll need motors.
Correct.
For the motors, we'll need ESCs,
Correct.
the equal amount of ESCs, and then we'll have a battery. With
Correct.
them, for connecting those, we'll need some wires
Absolutely correct.
and a receiver and a transmitter. That's it.
Wow, that's much of it, I would say. That's great. So transmit, okay, that's correct. But there's one more thing you missed, propeller, right? Propeller
Yes, yes.
also is actually included in the avionics. So that's most of it. So thank you so much. And so avionics, we are going to look at in the second step. In the first step, let's go on to deal with the battery. How are we going to select the battery, and how are we going to get its weight? So again, at this point, I'll like to ask you one more question. So you have phone batteries, you have batteries in your power banks, in your laptops, right? So there's one quantity that defines the battery. So what is that? Very popular quantity. Number. mAh, exactly. It is called battery capacity estimate. So battery capacity, that's basically what battery capacity is. So battery capacity is like in terms of more general understanding, it's like how much time a battery will be able to supply the current it is like intended to supply. So we'll already have 7.52 amperes of current, but also we had this much endurance, do you remember?
Yes, sir. Yes.
15.
Yeah. So this is actually the amount of time that our battery needs to actually work. And this is the current that the battery is supposed to supply. So the net battery capacity. So we have a relation here. So now this relation, I'll tell you about this relation. So MAH is simply current into endurance, and 1000 here simply means converting into millis, right? But this 2 here, we have taken an assumption. So there are 3 motors we have, right?
Yes, sir.
So the thrust motor is going to be running all the time, right?
Yes,
But
sir.
the other 2 motors, do you think they're going to be running all the time?
No, sir.
No,
No,
sir.
right? So the yaw motor is not going to be running continuously, and the lift motor is going to be also running only intermittently. So taking into account all the 3 motors, we have just taken a factor of 2 to make things easy for us, in this exercise. So this factor 2 takes into account all the 3 motors combined. So if you just plug in, what do you get?
3760.
Correct. 3760 mAh. So we've got a battery now. The next thing what we need to get onto is the weight of the battery. But for the weight of the battery, now we have the battery capacity with us. Also, we are confused about something, and I'll bring it up at this point: 2-cell or a 3-cell battery. So let's look at how do we select a 2-cell or a 3-cell battery, like, let's just verify. Were we so sure that a 3-cell battery would be perfect for us? Were we right at that point? So this slide will give an answer to that. So this is a graph of a number of 2-cell batteries of varying capacities, and it gives their mass. So it's a collection of discrete points, and a line has been fitted. So here we can actually calculate the mass of our battery by this equation. We have the capacity up there, you see, 3760. If you put it, what mass do you get for a 2-cell battery? This is going to be interesting. Please calculate.
$266.16.
That's correct. 266. So we're going to leave the decimal points because let's just say 266 grams. For a 3-cell battery, we have another graph, and the equation is obviously different. So I request you to please also come up with a number here.
So 404.
404.
404.
Yeah. Now this becomes interesting. In these 2 numbers, what do you observe? If you
Weight
compare,
difference.
huge difference, right? So now, do you want to go back to your decision?
No, sir.
No?
We'll go
Okay.
with 2-cell batteries.
With
2-cell
Sorry.
batteries.
2-cell. Okay, you suddenly changed now. So
So-
let me give you some facts to give you a little more perspective. So if you remember the previous sessions, we had calculated the mass of the fins, gondola, and envelope, right?
Yes, sir.
So I'll put those numbers in front of you. The fins, it was 126 grams, for gondola 65, and for the envelope 579 grams, right? So you
Yes,
see,
sir.
they're the same order of magnitude. In fact, the percentage differences are significant, right? So
Yeah.
if there's such a huge difference, it really means a lot for the airship. So that is why this is a dilemma for us. Although we thought earlier a 3-cell battery would be safe for us because we would have extra power, but now it's adding a huge weight. So what do you think? We said earlier something about these graphs, right? That these are not really sacrosanct or really scientific relations, but these are just fitted values, right? So we say here, we just assume that these are fitted values and there might be some margin here. So this 2-cell battery might be able to just suffice for the requirements of thrust that we have. And at this point, we say that we'll prefer a 2-cell battery. At least for our design exercise, this is the argument that we go ahead with. Are you satisfied with that?
Yes, sir.
So,
Yes.
Okay. And at this point, I'll also like to ask, because it's been a lot of time of just me speaking. So are there any questions you have until this point about anything that we have spoken?
Sir, what about the discharge rate of the batteries? It will also depend on the 2-cell or 3-cell batteries, sir.
Right. Yep. But you see, at this point, we are basically looking at the initial sizing. We are basically looking at arriving at the weight of the different components, right? So we have, as you've seen, the weights of fins, gondola, and envelope. So I mean, at this point, you would definitely go down into discharge rates, but we get the weight of the batteries only with capacities and such parameters that you have looked at. I mean, it does not really affect the initial sizing at this point. I mean, is that okay?
Yeah, it's fine.
But thanks for your question. Anything else? No? So shall we move ahead? Okay. Somebody is on unmute. Can I please request you to mute yourself? Yep. So we look at the battery, and I said that in the second step, we look at the avionics. So somebody had already listed a number of avionic components that we had. So we just look at them. So we are going to need a receiver. So for the receiver, we have taken mass of 30 grams, looking at the typical receivers that are fitted in airships of size, 4 meters or less. The battery we got, we have selected with 266 gram battery. Now this is interesting. For the thrust and lift motors, we got a weight of 38.66, so we're just taking it to be 38.7 grams at this point. Now, do you notice something here? We have taken the weights of thrust and lift motor to be same, right?
yes.
But do you think both of these are going to perform the same kind of function?
No,
No, sir.
No. So what can you say about the lift motor then?
Sir, lift motor will be working only when we need it, and thrust motor will be continuously working.
Right. So does that mean the lift motor would not require that much amount of thrust, right? It would not produce that much thrust, right? Or
Sir, that will depend on the direction and
yeah, that will
mass for it, sir.
right. But so in general, we can say that lift motor is would be less. I mean, in terms of what is required of the lift motor, it will certainly be less than the thrust motor. So that is how we could have saved a little weight on the lift motor by putting a lighter motor there. But at this point, as I said, we are doing a initial sizing and a design a simple design estimate. So at this point, we are, for the sake of commonality, we are taking same motors at in both the thrust and the lift applications. But the yaw motor, we have definitely taken it to be a smaller motor of half the size. And this is an abstract number. I mean, this is just a number which is, we did not have anything better estimate at this point, so we just took it to be half. All right. So wires, we just assume it to 20 grams, just a margin there for the wires. ESC, we took 3 ESCs of 15 grams again, so 45 grams there, and 3 propellers, 10 grams. That is what we looked at. So 30 grams of the propeller. So that's all. And could you please sum up? Could you please sum all the components and write what is the total mass of the avionics that we have?
One 1907.
Sorry, please can you repeat that?
1907.
Sir,
No, 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 that's not
487.7.
487.7.
Yep, we get that too. 487.7 grams. So kindly check your calculation again. So
Yes, sir.
that is what we got. And so do you think the avionics is a little heavy? I put some numbers before, right? Fins, gondola, envelope.
Yes, sir.
So it actually, so fins were 126, gondola was 65, and envelope was 579. So it is actually a little heavy, but it could even be heavier. So that could be looked on later. So this is what we arrive at, and let's move ahead with the figures that we have. So now this is just like all the parameters that you got before. So envelope, fins, gondola you had from previous tutorials. Avionics we have just now. This is the total or the empty weight of the airship that we have. So 1259.11. I hope you're aware what empty weight is, right?
Mass without payload.
Sorry.
Mass without payload.
Yeah. So actually, but so there's something more missing here actually. So I like to ask you. So what more weight do you need now in the airship? You just answered that partially by saying payload. But is there anything more you need now? Think. Are we
Sir,
done? Like
we will have to increase the capacity by 250 grams, which was our payload.
yes, that's going to be the payload. True. So payload is one thing we'll need to add. Is there anything else? You could also take the gas weight, right? The lifting gas.
Yes, sir. Yes, sir.
Yeah. So let's go ahead. Now we'd like to estimate the CG of an airship. So this is going to be the same simple exercise you have done even in school. So the components we have now, we know the weight of each component. We also know their location from, say, the nose of the airship. And moment arm. So what is moment arm? Anyone? How did we calculate CG for a system of discrete masses? Do you remember? Two masses placed, let's say, distance apart. How did you calculate the CG? Nobody? So I'll tell you. So didn't we multiply their mass with the location and add all of that up for all the masses and then divide by the total weight of the system, right?
Yes, sir.
Yes,
Right?
sir.
So we're going to do the same again. Moment arm is basically the weight of each component multiplied by its location. It's x. That is the moment arm. So we're going to add the moment arm of all the components and divide it by the total weight that we have. So a simple thing again, nothing complicated here. So for the envelope, can you please multiply these two numbers and tell me what is the moment arm that you get?
Nine 27.
Okay, that's correct. Avionics.
$634.01.
34.01.
Great. Fins.
$354.70.
Okay. And gondola.
$84.5.
84.5.
Okay. So finally, what we have is the total weight of all these components is 1259.11, which we looked at in the previous slide as well. What we need is now the total of the moment arms. So can you please sum all the moment arms and please tell me what do you get here? Right, 2000 point. Okay.
2000.8.
Okay, 2000.8. Thank you. So CG can be estimated by this relation, which is the sum of the moment arms divided by total weight. Can you again quickly do this?
1.5890.
1.58.
That's correct. 1.589. Again, something to look here. So can you look at the location of envelope and the answer that we get here? So CG of the
So we
airship
have to
is
add
actually,
location.
yeah. Sorry. Yeah, please go ahead. Okay, so basically the CG of the airship is very close to where the envelope's CG was there. So this is one thing to note. And also the CG of the airship is behind the avionics and also behind the gondola. Now I would like to ask you at this point, what if you're asked to change the location of the CG? So what strategies come to your mind to change the location of the CG of the airship?
So we will have to adjust the location of other components like avionics, fins, gondola to move
Other
the CG.
components? Really? Because that would mean, see, gondola, if you talk of gondola, so you have already fitted the gondola to the envelope, right? You have made all the attachments, you have fixed up everything, right? So it would mean
Yes, sir.
like tearing it up again. And
That-
similarly, fins and yeah.
Sir, the battery is the most heavier part in the avionics. So in normally RC aircraft, we tangle with the battery for the right center of gravity.
But what one point to note here is that battery would be, as you know, our gondola is pretty small, right? So
Yes, sir.
and
Yes, yes.
battery would there would be roughly no place for the battery to move around anywhere in the gondola. So wherever the battery is, it is there now. So a battery can't move anywhere now. Doesn't have any room because we don't have the luxury to move it anywhere across the airship, right?
Yes, sir.
So you can't move the battery. So what else? You can't move the fins as well. That means you're again changing the design of your airship that you have arrived at. Avionics. Avionics is again all the components that have been placed primarily in the gondola, right? I mean, you can't change the motors, you can't change the battery. Other components are very light, so they won't affect really. So I'll give you a hint. How do you do this in an aircraft? I mean, apart from the battery, don't think on those lines. But for an aircraft, how do you change its CG after you have completely designed it? After you can't change anything about the aircraft, and you're asked to change the CG, how do you do it for an aircraft?
Placing some dead weight.
Great. That's correct. Dead weight. But there's a technical name for that. Do you know?
Center of pressure.
No, the name for the dead weight. It's called, I'll tell you, it's called ballast. So we're going to have some room for ballast. That is basically essentially some dead weight that we're using only for the purpose of changing the CG after the airship has been designed. Now, you looked at one airship earlier actually, where there was a pocket, a kind of a space for keeping this ballast. And normally, so where would you like to keep this ballast? I'd like to ask you, where, at what location, what point in the airship would you like to keep the ballast? In the gondola? No, that really wouldn't change the CG much.
Sir, we will decide the location of the ballast according to the adjustment we require in the CG. Like if you have to move it forward, then we will do the required changes like that.
Yeah, that's one way. But actually, so what happens is, so ballast can actually vary in its mass. So dead weight you can actually vary, right? I mean, you can change its mass. So what we do is we keep its position fixed because it's always much more difficult to have a variable location, but it's much easier to have a variable mass. So, I mean, you have a fixed location in the airship. This is what I tell you. And a fixed location, you can vary the mass. So, where would that fixed location be?
At trailing edge.
Trailing edge. That's correct. But just the trailing edge, or somewhere else too?
Also the nose part, sir.
Correct. So both the nose and the trailing edge. So normally there are pockets or kind of designated spaces for keeping this ballast in both the nose and the trailing edge. Usually airships are tail heavy. So normally you keep ballast in the nose, but you could keep it either in the nose or at the tail. Why? Because that is where its moment arm would be the maximum, right? And that is how it can give maximum effect of having a change on the CG. Is that clear?
Yes, sir.
Right. So now we go ahead, having been talked of ballast, let's go ahead and actually see the payload calculations now. What is the payload that our airship can actually carry? We're done with everything. The only thing that remains is payload now. So for estimating the payload weight, or I may rather say how much payload the airship can carry, given we know its net lift and other things. We know the empty weight of the airship is this. We are assuming that the dead weight, we can put 90 grams of ballast in an airship, right? This is an assumption we are making at this point. So we have seen two LTA gases, hydrogen and
Helium.
helium, correct.
Helium.
So let's go around hydrogen. You got a net lift of 1602 grams earlier, right? So what would excess lift be? Can somebody tell a simple relation? Excess lift would be net lift minus. Yeah, please. Yep, you can go ahead and attempt. No negative marking. So, okay, it's simply net lift minus the empty weight of the airship minus the ballast weight. Can you please calculate what that comes out to be?
One 169.11, sir.
So sorry, that's wrong.
252.8.
Yes, sir. 252.89. You're getting it.
Yeah. So remember, we took hydrogen, and what we get is that our airship can carry this much amount of weight or payload, right? This is what it means, right?
Yes, sir.
This means our requirements of 250 grams of payload have been met. We were only required to carry 250 grams, right?
Yes, sir.
Yes, sir. Yes, sir.
But you might be thinking it's just barely carrying it, right? So that is something to again notice here. We have a very small margin of just 2.89 grams. So that's a pretty much small margin. So to counter that, I mean to increase that margin, what can we do? If I say like we want to have more margin here, a very simple thing.
Sir, we will reduce the
Gross
weight of
lift.
ballast.
Correct. So we can reduce the weight of the ballast. That is the most we can do at this point because we cannot change anything else that we have done before, right? Ballast is something that was actually manipulated after the design was complete. So we can actually reduce this number and we can have a more margin. If we do the same procedure for helium, now this is very interesting. Net lift, what we got was 1486 grams. Excess lift, the same equation. And what do we get?
$136.89.
Yup. So do you think the requirements have been met?
No.
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 So for the airship that we began with and for which we arrived at these numbers, remember we began with an airship that was of 3.5 meters length, right? And it was an NPL shape. And remember we took a velocity of 8 meters per second, right? The cruise velocity.
Yes, sir.
So for those those parameters that we began with, we cannot have helium filled in. We can only do with hydrogen. This is what we infer at this point. So, but again, now what if I say, no, I don't have the liberty to use hydrogen. If you're only supposed to use helium for this airship. So what will you do now? What will you do now? Like now you're allowed to go back in your design process and change something. What comes to your mind? What can you do?
Sir, then we will completely remove the ballast and we'll reduce some weight in the empty weight.
Yeah, you can't. Okay, first of all, you can't reduce the ballast. Ballast is always needed. Why? Because supposing your airship is not trimmed, you fly your airship and you find that it's not trimmed at the right angle, right? So you need
Yes.
something for that correction. So ballast you can't remove, but yes, you'll have to go into the empty weight. And this, I would rather say, is the content of the last tutorial that we have for this series. That would be taken by Professor Pant after this. And that would be much more exciting tutorial where you'll actually get to see all these numbers, how you can play around with these numbers. You will look at a spreadsheet where you will change the numbers and you will see that upon changing, how can we really affect the result. So that will be then coming after this. So we've almost reached the end. I'm going to sum up that our airship was an NPL sheet. We arrived, the length was 3.5 meters. This was a payload requirement. The envelope material we selected was a metallized polymer. Volume, it was 1.4 meter cube, but it's okay. We just went a little up above that. It's okay. And currently, the airship that we can build can only have hydrogen with it. Also, one thing to note is that this margin is pretty low. That is true. This margin needs to be more. So we should decrease the ballast weight. So we are done here at this point. So I'd like to ask you any questions you have about this exercise.
Yes,
I'll be happy
sir.
to answer. Yep.
So I have a question. Sir, can you please take back to the lift slide in that we calculated lift? Yes, sir. This
Yeah.
Sir, whenever I go with the RC aircrafts and all, sir, I struggle with the motors. Like motors can have same weight, but the output of the motors is different. And several times whenever I use ESCs with same configuration, the motor tends to give different outputs.
Okay.
So so in this case, how will we manage that thing? Yeah.
Right.
So maybe Shashwat, I can answer this question.
Please, sir. Yes, sir.
Okay, so see what happens is the power output and the thrust with the propeller from a motor is a function of the quality of the motor, and also, so what happens is if you buy from a very well established company, then the variability in the motors is very less. But what you say is right, that if you go to the local market and if you buy some BLDC motor, whatever is mentioned as the rated capacity, you may not get it. Okay. So what we have done is, while preparing this database, we actually looked at the motors, the data of the motors of very well established and very rugged companies, based on the experience of some of our previous aero modelers. Okay. So yes, there is a variability in everything. So you have to keep a margin in the variability. So therefore, for example, now we are getting exactly to 52.89 kilograms payload. I think this is going to be very risky, because you will build the whole airship and you find that there is some problem. So I understand your constraint, but that happens mostly when you go for non-standard equipment. When you go for standard equipment, then you do not see so much of variability.
Yes, sir. Sir, and also a question: the variability which we discussed about, sir, is there any method that we can rectify this? Because that is the most common method we get.
No, the only thing you can do is that you source your items only from reliable and well-established organizations, because their data will not change drastically. And if it changes, it will change for the better. So for example, if they say that the motor weight is 39 grams, it will be 39 grams or less. It won't be more.
Yes, sir.
But
Thank you,
yes,
sir.
but yes, like in every design, you need to have a robust design by keeping margins. So by experience, you come to know how much variability to expect, and that much margin. So my ballpark value is around 5%. Expect that what you will get is 5% heavier than what you plan and 5% lesser thrust, or motor will last 5% lesser watt hours. That way you will be able to get. But if you do it from a very reliable source, then the variability will be lower.